Hello, today we are going to have a look at sectors of circles, and we are looking at page 9 in our log tables for the tools available to us when we see the sectors of circles. So a cutout of a circle is a sector of a circle, and if we ever see a cutout of a circle, we're going to open up page 9 so we can see the tools available to us, because we know for our area and volume type questions, the real key skill, or one of the key skills, is if I recognize I have a particular type of shape, I'm going to write down the relevant formula and then see if I'm able to sub into it. And if I can train myself to do that, I can get through most questions. So the two formulas are based on the fact that we're dealing with fractions of circles. So if we have this little sector, this little cutout of this bigger circle here, we've effectively got a fraction of the complete circle. If we started at this line and rotated all the way around, we'd cover the entirety of the circle, and the area of that would be pi r squared. But we're dealing with a fraction of a circle. We've gone around by a particular angle theta, and that fraction of a circle is going to be theta all over 360 if we're dealing with degrees, or it would be theta all over 2 pi if we were dealing with radians. And these questions can often involve either radians or degrees. We have both versions of both formulae that we need here. The other thing to note is our arc length. So L is our arc length. That's our L, and it is effectively a fraction of the circumference of the circle. So we have our fraction of our circumference formula. And again, both of these look neater in radian form, but both formulas work exactly the same way. It's just that things cancel out a little bit when we're measuring in, when we are using the formula in radians, but you'll get the same answer so long as you're working in either degrees or radians. Either is fine. To give a basic reminder and introduction to our formula, I'm going to get the arc length and the area of this sector here with a radius of 2 and an angle that we're dealing with of 90 degrees. Purpose of this is just to use the formulas before we get into a more advanced exercise. So if we want to find the arc length of this sector here, what we're really being asked for, and we need to draw this in when we have it on our sketches to reinforce the language, because we don't often talk about arc length. We're looking for the L on page 9 in our log tables. So if we're talking about arc length, that's what we have to know we're looking for. So I'm going to write down my formula. I can see I'm asked about the arc length of a sector. So I'm going to write down that formula, and I'm in degrees, so I'm going to write the degrees version of that formula. And this is our setup. We're always going to be writing down our formula. So we're reinforcing it so that when we come to the exam, we'll be able to figure out what formula we have because we've got that reinforcement sorted. So we're always writing this down so that it's constantly set up in our heads for when we need it later on. So in this case, it's fairly straightforward. We're going to write in that we have theta is 90 degrees and or is going to be 2. So that's all we need to sub in here because pi is just a number, even though we use a symbol for it. So 90 out of 360 on 2 pi times 2. And we just get pi, and that would be units because it's a measure of length. We're going around the circle, we're measuring this length. Often this will come up in the context of the perimeter of shapes, as it will here, and we need to remember that we're dealing with a length when we're dealing with L. We're also asked for the area, so let's write down the area formula, and again we're going to use the degrees version of that formula. And we're going to write down what needs to go into that formula. So now we have everything set up, so we definitely don't make any errors, and we definitely get all of our marks for our work because it's very clear what we're doing. 2 squared. And that I think is going to be pi again. 4 1/4. Yeah, as it happens, that ends up being pi as well. And this is going to be units squared. Now in this case, I didn't give any criteria as to whether we would go to 1 decimal place or whether we would leave things in terms of pi. So I have just left it as seemed convenient in the question. And that's fine if we're not given any specific requirements. But watch out for restrictions in the questions. And I've put those restrictions in here now. Now, let's have a look at this more advanced situation. So we've given us a little bit of a story. The template of a large funnel looks like this. So we have a funnel, and we're going to take this side, and we're going to fold them up so that those edges meet each other, and that is going to form a funnel. And it's important that we try and build our physical intuition for being able to fold a shape like that, because it can come up directly in an exam question. The ability to take a diagram and move it around in your mind is part of what is required. So a lot of the time, the maths in these won't be as daunting as they are in some other areas of the course, but that ability to take a shape and to manipulate it and to understand the components of it is key to being able to do these types of questions. So take the time when we're looking at these and really visualize the parts of the shape so that when we come to exam questions that look a little bit different, we can still break it down in the way that we need to. But let's get on with our question. Part 1, find the perimeter to 1 decimal place. Part 2, the area in terms of pi. And part 3, the radius of the larger rim when the funnel is formed. So the perimeter of the shape to 1 decimal place. So the perimeter, regardless of what type of shape we're talking about, is just the distance all the way around. So we add this length to this length to this length to this length. So I need to name some stuff so I can start looking for it. And I am going to call this, well, L is the name for, I recognize that these are parts of circles. So I'm effectively dealing with kind of 2 sectors. I have a little sector here, the bit that's missing, and then I have the larger sector going on out here. So this is going to be the arc length of the larger sector. This is going to be the arc length of the missing sector, the little sector or the small sector, and this is going to be the difference between the radii of our bigger and smaller sectors. So I'm going to call this distance x. I'm going to call these 2 L's, and we'll call this L1 and L2. You can name them whatever you like, but try to keep them as sensible as possible. So calling these L would make a good deal of sense because we are looking for arc lengths. Now, perimeter. So x is probably the easiest one to find off the bat. We know that x, so part 1, this x length is going to be the same for both, and it's going to be 27 minus 9 meters. And L1, we write down our formula. We're given our angle, our theta, in radians this time, so we're going to write down the radians version of this. So or theta is equal to 27. For L1, it's going to be the larger radius. And theta is our 2 pi over 3. And that ends up being 18 pi. Again, that's in meters. It's often a good idea to just leave pi in during a question because this is the exact value, and carrying around awkward decimals really isn't worth the hassle a lot of the time. If you can leave it in this form, if you're comfortable with that, it will probably be better for you. L2 This is the smaller sector, the bit that's effectively missing from our larger sector. So this is how we're going to get L2. It's going to have a radius of 9. Same angle. And that ends up being 6 pi meters. Those are the different parts that I needed. So I have x plus L1 plus x plus L2 gives me the perimeter of my funnel template. So that's going, the perimeter is going to be x plus L1 plus x plus L2. Very good. It's going to be 18 plus L1 is 18 pi plus 18 plus L2 is 6 pi. Ends up adding up to 36 plus 24 pi, but we were asked for our answer to 1 decimal place, and that happens to work out to 111.4, and we remember that we're dealing with meters for perimeter. Now part 2. We look at what we're asked for. We're looking for the area in terms of pi. Well, the area of this shape is going to be the area of the larger sector with the smaller missing sector, the dashed sector as I've written it here, removed. It's going to be the area of the big one minus the area of the small. This is a fairly common thing that comes up in sector type questions where you have the middle bit or the inner part of the sector missing. So when we do that, we write in our, actually I could call that area, no, that's fine. So area big is going to be write down our formula again in radians version. It's going to be half on 27 squared on 2 pi over 3. So being equal to 243 pi, and then the area of the small. Again, write down our formula. It's going to be 9 for the radius. It'll be 27 pi, and then our area is going to be 243 pi minus 27 pi, ends up being equal to 216 pi. Now the final part, we're looking for the radius when we form the cone. Well, if we, as say, wrap x over to x, we would end up with a funnel shape as this, and we're asked for the radius of this larger rim, this upper rim here. Well, that means that at the circumference C of our larger rim is going to be the same as L1. So we know that 2 pi r, the radius we're interested in, is equal to L1, which we found to be 18 pi. So we rearrange and we get r is 9 meters. And that's what we need. This type of question is primarily about being able to visualize moving that shape around. And that is what we need for sectors of